Hey everyone, welcome back to Calculus 2. This will be lecture 27 of the course. And in this lecture, we're going to discuss two very powerful tests for convergence. This will kind of be the last lecture. This will be the last lecture in a series of lectures where we've been interested in when do certain series converge, how can we explore this question, what are some tests that we can do, etc. So this we'll still be using these tools for the rest of the course, but this will be the last one where we introduce these brand new tests, these convergence tests. So and we kind of end on a really good one, right? So the ratio and root tests. Okay, so let's go ahead and jump into it. So we'll go ahead and call this section 4.6 the ratio and root tests. Okay, and the first thing we want to do is define well, we want to distinguish between absolute and conditional convergence. So this is something that kind of is hinted at in the previous lecture when we talked about alternating series, but we formally defined it here. All right, so let's start with that. What we say is that a series A of n is absolutely convergent if the sum of the absolute value series converges. Right? That's what we mean by absolutely convergent, absolute convergence. And then contrast that with a series A of n being conditionally observant or convergent. So conditionally right, so a series A of n is conditionally convergent if sum of A of n converges. Right, so it converges, but its absolute value does not. Right, so its sum of the absolute value diverges. Okay. Right, so two distinctions there. So on the one hand, you've got this idea of absolute convergence. And so a sequence is absolutely convergent if its absolute value converges. Now, if this happens, then this automatically happens. Right? You might recall that from the last section. Right? So if the absolute value series converges, then the original series converges as well. Now, what we're kind of introducing here is this idea of conditional convergence. So a series is conditionally convergent if it converges but its absolute value diverges. Now, what can frequently be happening here is, you might have convergence of the sequence itself, but if it's like an alternating series or a series where you have a significant number of negative terms, like half of the series is negative, then the convergence may depend upon the negative values being negative, right? So they may cancel each other out, undo each other, and if you take that away, then the series may diverge, right? So that's more often than not, that's the driver, right? That's the driver behind conditional convergence, right? The necessity for the negative terms to be included as negative terms so that the total sum will converge. Okay, let's do an example kind of demonstrating this property. Right, so let's consider consider this guy here, n equals 1 to infinity of negative 1 to the nth power divided by the natural log of n plus 1. Okay, now this is a relatively simple series to write out. This is going to be negative 1 over natural log of 2 plus 1 over the natural log of 3 minus 1 over the natural log of 4 plus so on, right? So the negative, the terms oscillate, right, back and forth. It's alternating. Okay, so it's an alternating series, so we can use the alternating series test to test for convergence, right? So by the alternating series test, right? So by the alternating series test, we know that a of n is less than or equal to, sorry, it's a reverse. A of n plus 1 is less than or equal to a of n. And the limit as n goes to infinity of a of n is equal to 0. So this series converges. Right, so again, I'm kind of going fast here. You could confirm these things by looking at the series. You could figure this is definitely true, this is definitely true. So this is straightforward. Right, so by the alternating series test, we have these two conditions met, so the series converges. Okay, but consider the absolute value series. Consider this absolute value series, right? Now we're just going to use direct comparison on this, right? Well, let's write it out here first. So when we take the absolute value of this, that basically nullifies the negative, right? So you'd end up with just 1 over the natural log of n plus 1. Okay. By direct comparison, and we could compare this directly with the harmonic series. Right, by the harmonic series, 1 over n, I think would work. And we would see that this thing diverges. Okay, so we would see that this series diverges. Right, so and so basically the punchline of all this is really the details aren't what we care about in this example. What we care about is the the fact that this is going to actually be a conditionally convergent series. So since the original series converges and the absolute value of the series diverges, this series, the original series, is called conditionally convergent. Right, so it doesn't converge in absolute value, but it converges. The original series converges. So what we're really interested in here, at least for this section, is the absolute convergence case. All right, so what we want to do is next we're going to look at a theorem that provides a test for absolute convergence. Okay, so this is called the ratio test. Okay, this is the ratio test. And I'll just write that in here because we'll be using this a lot in the coming sections. We'll need this a lot when we get into power series and Taylor polynomials and towards the end of the class here, or towards the end of the course. So let's let the sum of a of n be a series with non-zero terms. Okay. If that's the case, then 3 things. All right, the first one is the most interesting one, and that says that the sum of a of n converges absolutely if the limit, as n goes to infinity, of the ratio, this is why it's called the ratio test, of a of n plus 1 over a of n, if that limit is less than 1. Okay, so the series will converge if the absolute value of the n plus 1 term divided by the nth term, the limit as n goes to infinity of that absolute value is less than 1. Then you get absolute convergence. Okay, now you get divergence. Okay, you get divergence if the limit is greater than 1, okay, or infinite. I'll just write or infinite, right? If the limit is infinite or any value greater than 1. Right, so anything, basically anything other than 1 or less. If it's like 5, or if it's 57, or if it's 1,010,000, or if it's infinite, then you're going to have divergence. The series A of n will diverge. And then you've got inconclusive if the limit of the ratio is equal to 1. Right? If you've got equality, then you don't know. Right? And the series could converge, it could diverge, you don't know. It doesn't help you. So you have to move on to a different test. Okay. So this is the ratio test, and this is a nice, really nice test. It's pretty simple, right? And it works for a lot of series. It's very useful, mostly because the nth term and the n+1 term are going to have a lot of things in common. So when you divide one by the other, you get a lot of cancellation, and you get generally, well, if it's a complex, terms are complex, this can be a simpler limit to evaluate. So let's go ahead and prove the first part. Okay, so usually in Calculus 2, I try, anyways, to kind of ramp up the volume of proofs. I like to give at least one good proof every lecture, because we're getting ready for Calculus 3, and then after that we're getting ready for the math courses where proving things is the point. And so the beginning of the course, we maybe had a proof once every 3 or 4 days, every 3 or 4 sessions, and towards the end of the course, it should be every time, in my opinion, just because we're really trying to gear up. We want people to be maximally exposed to these things. Okay, so let's prove the first part. Right, the other parts I don't know if they're hard. I've not done it myself, but the first one I've seen before. It's the most important part of it. And so let's take a look at it. So what we're going to do is we're going to assume that the limit as n goes to infinity of the ratio a of n plus 1 over a of n is equal to some value r, and that value is less than 1. Okay, that's our assumption, right? So that's basically the condition that we need, and if that's true, then supposedly this series will converge, and that's what we need to show. We need to show that this implies absolute convergence. Okay, so assuming this is true, let's choose r, right, a real number r, such that well, a of n plus 1 over a of n is less than r. Oh shoot, I'm sorry, let me step back, I skipped a line. Such that, okay, forget about that part first. All right, so we're choosing r, big R, real number, such that 0 is less than or equal to little r, right? So we know that's true. And I think that should be strict. Let's keep that strict. So 0 is less than r, which is less than 1, and we're going to choose a big R between those two values, right? Strictly between them. Okay, we can do that, right? These are real numbers. R is some number that's less than 1. There's always going to be some other number between r and 1 if r is indeed less than 1. Okay, and so we can do this, right? So this is straightforward. Then where I meant to go with this previous one was to say that there exists an n greater than 0, right? So some positive integer such that the ratio of a of n plus 1 over a of n is less than r, your chosen r. Right? So the ratio is less than r for all n greater than this hypothetical positive integer n. Okay. So basically what we're saying is, we know that the limit of this is equal to some little r, which is less than 1. We're going to choose a big R between those two numbers, right? And we know that it's possible to find a natural number or positive integer such that the ratio is less than r for all n that are larger than this big N. Okay, then we have the following. Okay, and so here's this part's a little bit tricky, so let's be very careful with this part. You may have to pause it, back it up. So if a of n plus 1 over a of n is less than r, right, then I'm just going to rewrite this very carefully here. Right, then that, right? And these are both positive numbers, and so this is going to imply that a of n plus 1 is less than a of n times r, whatever r happens to be. Okay, and so this is the part that we're interested in. Okay, now we can do this again, right? We could also say that a of n plus 2 over a of n plus 1 is less than r, and that's going to imply basically the same thing, right? It's going to imply that a of n plus 2 is less than a of n plus 1 times r. Right, so that's true. Okay, and we could keep going. Right, a of n plus 3 over a of n plus 2 is less than r implies that. Okay, so we could keep going. Right, and so by doing that, by generating this series of inequalities, we get the following. We get this. Right, this is the first one we saw. Okay. Now we saw secondarily, pull it back up here, that this was true, right? Right, so that a of n plus 2 is less than a of n plus 1 times r. So we could take this one and toss it in there. And what we would get next is that a of n plus 2 is less than a of n plus 1 times r, which itself is less than a of n times r squared. All right, we could do it again, right? We could continue on like this. Okay. And so on. Right, we can continue on. Okay. And so we can construct from this we can include elements of this and create a geometric series. And so the geometric series, okay, let's write this out carefully as well. So this would be absolute value of a of n times r to the nth power, right? So this is going to be n equals 1 to infinity, right? And so this is going to be equal to what? A of n times r plus plus a of n times r squared plus ... right? And this goes on and on. This is going to converge, right? This series here will converge. Right, and it'll converge because, r is less than 1, right? By assumption, right? Recall back here at the beginning, right? How did we come up with this r? Well, we chose an r that's between, our limit value and 1. So this r is less than 1. And so if that's the common ratio of a geometric series, then the series will converge. Okay. All right, so then by the direct comparison test, okay, the series, and here's another one, we got to be really careful here, n equals 1 to infinity of a sub big N plus a little n here. Now, little n is the index, big N is, you can think of it as a constant, right? It's a fixed n that we have chosen such that all of these inequalities hold. All right, so this is going to be equal to a of big N plus 1 plus a of big N plus 2 plus dot 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 plus, and I'll put the nth term in here, a of big N plus n plus dot dot dot. Okay, this is going to also converge. Why is this one going to converge? Because of the inequalities we just set up, right? The inequalities we just set up. Okay, so a of n plus 1 is less than a of n times r. A of n plus 2 is less than a of n times r squared, right? So term by term, these will have this. The direct comparison is going to work here. Oh, sorry, these are greater than, less than, yeah, right? These are less than. So if this one converges, if that one converges and all of the terms are smaller than this, then this one is going to have to also converge. Right? That's the direct comparison test. Right? So this is extremely tricky and subtle, right? So you have to make sure you get this. Right? The only reason we did this was so we could set up these inequalities so that we can make this term by term comparison. Okay, so this term is less than this term is less than that term, and so on and so forth, every term in the series. Okay, and so that means this converges. Now, what does this imply? Well, this implies that the overall series converges. Right? This implies that the series itself converges. Why does that work? Why does this work? So why? Why does that make sense? Well, hopefully it makes sense, because basically these two series are the same, except for this one is missing the first big N terms. It's missing a finite number of terms up front, right? And so that's not going to impact the convergence of the series, right? All right. Let me write this in. So because discarding a finite number of terms, right, namely n equals big N minus 1, does not affect the convergence of the series. So I've said this before, but let's mention it again here. It doesn't matter what the first 50 terms of the series are, or what the first 1,000 terms are. It only matters what comes between 1001 and infinity, right? You have to take into account that we're really talking about infinity here. We're talking about an infinite series, right? You just keep adding and adding to it. So the first 50 terms don't matter. That's definitely finite. No matter what, the first 50 terms is always finite. You can't have an infinite, you can't add up to infinity in the first 50 terms or the first 1,000 terms, right? So no matter what they are, they're not going to affect the convergence, right? So if I can prove that this series converges, then that's going to imply that this one must as well. Whatever those first 50 terms are, or first 1,000 terms, you just add it right to it. It's a finite number plus a finite number, so you get a finite number. Okay. All right, and so that's that, right? So what do we have here? We have that this thing also converges. And so that implies, consequently, by the absolute convergence theorem, all right, the series converges, right? So if you've got the absolute value of a series converges, the series itself must also converge. That's a fact that we established like quite a ways ago, I'd say back in maybe in section 4.2. The very beginning when we started talking about series, right? The reverse is not necessarily true, right? The original series converging doesn't imply that the absolute value converges, but the absolute value converging does imply that the original converges. Okay, so we've got the absolute convergence then. Okay, kind of a beautiful little theorem, nice little proof, extremely tricky, right? A lot of math proofs, if you start to go climb higher into the into the ranks will involve things like this, constructions like this that require some thought, that require some convincing, perhaps, but the argument is solid. So take a second. If you weren't following this piece, just take another look at it. All right, perfect. So let's take a look at some examples using the ratio test. Very powerful test, extremely useful. We use it all the time. Example. Let's consider this series, n equals 0 up to infinity of 2 to the nth power over n factorial. Does it converge? Does this converge? Well, let's just try to use the ratio test. Okay, what does the ratio test say? Well, the terms have to be non-zero. That's pretty much it, right? And so obviously non-zero, right? The n equal 0 factorial is 1 and 2 to 0 is 1, so, and everything else is definitely positive. So non-zero terms. So let's take a look at this. This is what we need to look at. Limit as n goes to infinity of the ratio of the n plus 1 term to the nth term. Okay, and so the n plus 1 term would be 2 to the n plus 1 divided by n plus 1 factorial. And instead of making a fraction over a fraction, I'm going to do a fraction times the reciprocal of the fraction. And so the a of n term would be, I really need the 1 over the a of n term. And so we get n factorial over 2 to the n there. And a lot of really nice cancellation occurs here. Okay, so 2 to the n plus 1 over 2 to the n is just 2. So you get a 2 up top. And then n factorial over n plus 1 factorial. Well, it turns out that's just n plus 1. Now be careful, make sure you understand that. That's a mistake, that a lot of people in Calculus 2 make when they start dealing with these factorial expressions. They'll start canceling them wrong. So I'll just do this once just to make sure that people are following. Right? So what do these things mean? Well, I've got 1 times 2 times 3 times ... times n minus 1 times n on top. And then on the bottom I got the same thing. Except I got one more, don't I? All right, this one goes up to n plus 1. And so everything cancels except the n plus 1. All right, so that's why you have that left over there. And so this guy here clearly goes to 0. Okay, and so that is good enough. That's what we needed to see. And so we would say, therefore, the series converges, and converges absolutely. Okay, and this is by the ratio test. I better put that in there. Right, because that's what this thing here is. Right, taking the ratio of the n plus 1 term to the nth term and evaluating the limit as n goes to infinity. What happens to that when it gets really big? Okay. All right, perfect. Let's take a look at another example. How about this one? N equals 0 up to infinity of n squared times 2 to the n plus 1 over 3 to the n. Does this converge? Again, let's just jump right into the ratio test. Everything is non-zero for sure. So that's what we need to check. And then we just try it. Okay, so what do we get here? We get the limit as n goes to infinity. And now we have to write in the n plus 1 term first. So that'd be n plus 1 squared times 2 to the n plus 2 power divided by 3 to the n plus 1 power. Okay, and then we're going to take that divided by a sub n, which is just this, and so I'm going to reciprocate that and multiply. So I'd have 3 to the nth power, and then down here it's n squared times 2 to the n plus 1. Right, now this is all just, everything's positive here, so the absolute value is not really important, so we can drop that and just make those brackets. And what can we simplify? The nice thing about this method is that very frequently it results in some pretty good simplifications. So the 2 to the n plus 2 divided by 2 to the n plus 1 is just 2. So we've got a 2 up top. Now we're stuck with the n plus 1 squared. What about the 3n? And that means we're stuck with the n squared on the bottom as well. All right, so I'll put that in there. Now what about the 3's? Well, same thing, so you get a 3 there, don't you? All right, so let me rewrite this slightly. Now, the thing to notice here is that, and you could verify this by just expanding this n plus 1 quantity squared here, but this is going to be a second degree polynomial up top, and the leading coefficient is going to be 2. Right? This is going to be 2n squared plus something or other. Right? But the fact that it's 2n squared on the top and 3n squared on the bottom means that the limit is 2/3. Okay, and that's less than 1. Right? So the series converges. Okay? Right? Perfect. So the series converges by the ratio test. Okay. Let's see, one more example. Let's take a look at one more example. Okay, so the last example, let's take a look at this one. Here the series we're interested in is n equals 1 to infinity of n to the n divided by n factorial. Now we're talking serious growth here. My guess, and I don't know, well I kind of do know, is that this is going to diverge. But, you know, these are both going to grow fast, right? It's a question of which one grows faster. So you've got n raised to the nth power, so that's 1 to the first, 2 squared, 3 to the third, 4 to the fourth. Down here you got a factorial, which grows pretty quickly as well. So let's take a look and see if the ratio test can help us with this. Okay, and so nice thing about this is that it becomes very easy to deal with these kinds of things with a test like this. It is very robust. So plugging in our n plus 1 term and then multiplying by the reciprocal of the nth term, we get this and then this. Right now everything is positive here, so its absolute value is not necessary. And let's see. Yeah, we can do a little simplification here right out of the box. The n factorial and the n plus 1 factorial will cancel, right? And I'll have n plus 1 to the n plus 1 power over n plus 1, and then times 1 over n factorial. Okay, now what happens to this? This is equal to the limit as n goes to infinity of n plus 1 to the nth power, right? There's a cancellation that occurs there, divided by, hang on one second. I might have made a mistake here. 1 over, this should be n to the n. Sorry about that. Yeah, the n factorial was in the top, right? So this should be n to the n down here. And so this will be over n to the nth power. Okay, and we can, since everything is exponentiated with an n, we can rewrite this again as the limit as n goes to infinity of n plus 1 over n raised to the nth power. And we can see what happens here, right? So inside here, let's divide everything by n. And we'll get, well, no, sorry, let's break it up. That's what I meant to say. N over n plus 1 over n to the nth. And we'll have 1 plus 1 over n to the nth. And so what is this, right? Well, this is one that we've seen, right? And you may have to go back. I don't recall which lecture it was, which section, but this is one that we saw. And what we saw was that this was equal to E. So this is the constant E. Okay, and now that E is 2.4 something or other, and so it's greater than 1. And there it is. The series will diverge. It's quite amazing, right? So this nasty looking expression that has all of these, n raised to the nth power divided by n factorial. That thing right there, when you run the ratio test on, you get E, right? So basically the ratio of the terms, successive terms, converge to E as n goes to infinity, which is amazing in and of itself. And then of course that will imply what we suspected ahead of time, that the series will diverge. Okay. All right. Very good. Very good. Now, this guy here is something that we could have used, the theorem that I'm about to introduce. We could have used what's called the root test on this. I don't recall off the top of my head how we showed that this limit approached E. But I do believe the root test, which we're about to introduce, would probably tell you at least that it converges, or that the root test is for series, but a term like that would work for us with the root test. But anyways, so that's the last example. Let's jump into the root test. So this will be the last test that we formally introduce. We may see some other techniques, but this will be the last one that we formally introduce. Is called the root test. Now the root test is called the root test because it has a nth root in it, right? Now before you freak out, because nth roots are nobody's favorite, the root test is extremely powerful, especially when working with series that involve nth powers, kind of like what we saw here, right? So if this were a series, 1 plus 1 over n to the nth power, I would certainly try to deal with this using the root test initially, because it's just perfect for that. Okay, which is kind of what I was trying to say there, but I misspoke. Okay, so here's the root test. So let the sum of a of n be a series. All right, so there's any series. Okay, then we've got the following conditions. The sum of a of n converges absolutely if the limit as n goes to infinity of the nth root of the absolute value of a of n is less than 1. So that's one that probably you didn't expect, right? But yeah, so if the nth root of the absolute value of the terms of the series converge to 1 as n goes to infinity, if they head off to 1, then, or less than 1, any value less than 1, then the series must converge absolutely. Okay. Secondly, next comes the divergence condition. So this will diverge if, similar to the ratio test, the limit as n goes to infinity of the nth root of a of n is greater than 1 or infinite. Right? If the nth term, absolute value of the nth term, taking the nth root of the nth absolute value of the nth term is infinite, then the series will diverge. And then just like with the ratio test, inconclusive if the limit as n goes to infinity of the nth root of a of n equals 1. So if it's equal to 1, then there's nothing that can be said. But if it's less than 1, we can say something. If it's greater than 1, we can say something as well. Okay. So I'm not going to prove this one. just because it'll take a little more time than I want to, but I think you can find it online. Just look for proof of the root test or try to work it out yourself. You might be able to employ some of the techniques. I just don't know. I haven't seen this proof myself, at least not recently. Let's do an example with it though. Okay. We're interested in this series n equals 1 to infinity of e to the 2n over n to the n. Does this converge? Okay, well, let's talk about the absolute value of a of n, right? That's the terms itself, so e to the 2n over n to the n. Okay, and what about the nth root? Well, that's going to be e to the 2n over n to the n. And instead of using the radical notation, I'm just going to use the 1 over n notation. Okay, so we'll write it like that. Right, and then this is where the root test becomes extremely useful, right? Because you're exponentiating everything with 1 over n. So if you've got n's in the exponents, it's going to clean up nicely. So e to the 2n over n to the n over n, right? And you get e squared over n. So the limit as n goes to infinity of the nth root of the absolute value of a of n is just the limit as n goes to infinity of e squared over n. Right, and now I hope everybody can see what happens here and can intuit what happens here. If not, I feel I have failed as a Calculus 2 instructor. This is obviously going to go to 0, right, which is less than 1. Right, n is going to grow without bound. E is a constant. Clearly, this is going to, this limit is 0. So because the limit is less than 1, right, the series converges. Okay, so that's that. Sorry, I should say it converges absolutely. Okay, and that's the root test. So that is the root test. Okay, we'll do another example in a moment, but let's pause for a second and reflect on what we've accomplished over the past 5 or 6 lectures. All right, so we have looked at 10 different tests for convergence. Right, so we have looked at 10 different tests for convergence. There's a lot of things we can try. We had the integral test, we had p-series, geometric series, ratio test, root test, absolute, direct comparison. What else do we have here? We had tests for alternating series. We had telescoping series tests. Right, so a whole bunch of 10, in fact. Knowing when to apply these things and in what manner to apply them, how to apply them, what order, how to think about this is a matter of practice. Right? It's a matter of just trying a lot of different things, getting very comfortable with a handful of them, being familiar with others. But there's no quick list, in terms of like, here's what you should do, and in this order. You really need to practice. You really need to look at lots and lots of different series, try to troubleshoot them. You need to try and fail on a bunch, right? And because you'll learn from those. But it really is a matter of practice. Now, that being said, am I going to give you guidelines? Yeah, of course I am. That's what I'm about to do. So guidelines for testing a series for convergence. Right, now you may have your go-to test, like maybe, if it were me, ratio test would probably be my go-to test if I can use that. If that one doesn't work, or I get an inconclusive, or I can't find the limit, or I get something, it doesn't work out, then, maybe I look at the integral test, or maybe I do a direct comparison, right? So here's how I would approach it, right? Here's a good way to approach it, a disciplined approach. So first thing to ask yourself is this: does the nth term approach 0? If not, the series must diverge. Right, so if you can automatically show that the limit of the nth term is not 0, then the series must diverge. Okay. Second thing I would look at is the series one of our special types? Right? And I'll just put special here. Right, is it geometric, p-series, alternating, telescoping? Right, is it one of these types? If it is, even if it's a rather exotic version of one of these, if it's a really exotic geometric series, but you can see that it is in fact a geometric series, AR to the n, you can apply the theorems for those series specifically, and they're very easy to recall or look up as needed. Okay. Next up, and then comes a special test, right? So, and in no particular order, can the integral test, ratio test, root test, etc. be applied? All right, so then start to think about the specialized test. For me personally, I would run right to this one. I find that to be the most straightforward, easiest to use most often, right? But if it has a certain form where everything is exponentiated with an n, root test might be the way to go. It might simplify things dramatically, really quickly. And it's it's very much like the ratio test in terms of the way it works. But and then finally, this is the hardest way to do it is to create a comparison, like a direct comparison. Sometimes this is hard. I think it requires a certain kind of thinking. It's not necessarily hard. It's just something you have to kind of used to doing. But can the series be compared to one of our special types? All right, so we have these special types. Can we compare it to one of them? Okay, so these would be good guidelines. Again, you can do it your own way. You should do it your own way. But maybe consider thinking about this approach if you're presented with a series and you have no idea what to do. This would be a good way to approach it. Okay, now what I'd like to do next is just do a couple more examples, kind of spanning, look at a couple series and use some different tests that we maybe haven't seen for a little while, just as a kind of a refresher. All right, so this won't take long. It's kind of simple ones, but just to remind people. Right, so the first one we want to look at is the sum from n equals 1 to infinity of n plus 1 over 3n plus 1. Right, and the question is, does this converge? Well, here's where the nth term limit can just come into play really quickly. So just notice that the limit as n goes to infinity of n plus 1 over 3n plus 1, we know that's equal to 1/3. It takes a second to check. Right, this is not 0, and so that's going to imply divergence. Right, that's just the nth term limit test. I think it's one of the first ones we learned. I can't recall if we actually called it that or what did we call it. That doesn't probably matter, but it was one of the first sections where we talked about these, and this was one of the first theorems we had. I believe we called it something like the nth term. I'm looking back right now. Yeah, limit of the nth term. Okay. So this is the limit of the nth term test. All right, so real simple, easy to see. Okay. What about this one? N equals 1 to infinity, the sum of, and then it's pi over 6 to the nth power. Well, the pi over 6 might throw you, but this is a geometric series, right? right? So here you would, if you think of the geometric series as AR to the n, well, in this case it's 1 times pi over 6 to the n, right? So r is equal to pi over 6, which is less than 1. And so the series, so you might not recognize that. This is 3.14 divided by 6, so that's less than 1, right? It's like 1/2. And so the series, would converge. Right? And in fact, for a geometric series, we can find the sum pretty quickly as well. Right? So in this case, the sum would be equal to a over 1 minus r. Right? So, yeah, a equals 1, r equals pi over 6. You can plug that in and find the actual sum of the series. All right. Another example. So the sum n equals 1 to infinity of n times e to the negative n squared. Does this converge? Well, when I see this, even though I kind of know where I'm going with this, but this would be one where it looks like an integral to me. It looks like an integral that we've done in the past even, right? So the integral test. I mean, you could try all the other things as well, right? Maybe to look at the limit of the nth term. I'm not sure. It's going to be n divided by e to the n squared. So I'm not sure what that would amount to. It might go to 0. I don't know for sure, but we can easily integrate this. So the integral test, I mean, if you recognize this as being, something that we've looked at with integration for, most of the semester, you might recognize this would be a simple u substitution to calculate this. So let's do that. All right, so the integral of 1 to infinity of x e to the negative x squared dx. Okay, and so we could integrate this, right? We could write this as, we're going to need a 2 in there, so 1 to infinity of 2x e to the negative x squared dx. Right, and then so just kind of coming off to the side, you'd let u equal negative x squared, du equals, well, let's make it just x squared. So then du is 2x dx. Okay, and so this would be 1/2 times the integral from 1 to infinity of e to the negative u du. Okay. And so we could, this is an improper integral, so we would have to, do something like this. 1/2 times the limit as b goes to infinity of 1 to b of e to the negative u du. And we would see that this is, 1/2 times the limit as b goes to infinity of, and then the integral here is negative e to the negative u, and that's 1 to b. Right? And so 1/2 the limit as b goes to infinity of, and now remember the u is x squared, so this is negative e to the negative x squared from 1 up to b. Okay, so last one we can get in this one. So it'll be negative e to the negative b squared minus, so minus negative e would make it a plus e to the negative 1. Okay. And so we can kind of look at this and see what's going to happen here. So basically this one is going to go to 0 as b goes to infinity, right? Because this is e to the negative b, so that's 1 over e to the b, right? So the e to the b is in the denominator, so it's going to grow. Numerator's constant, -1, so that's going to be 0. And then this will be 1 over e. Okay, and so this would ultimately, I believe, this would be equal to like 1/2 1 over 2e, something like that. Okay. So at any rate, it's less than infinity, right? So it's a finite number, and so the integral test says that, hey, first of all, these terms are positive and decreasing, and the integral converges, and so the series must converge as well. So the series n equals 1 to infinity, n e to the negative n squared is less than infinity as well. Okay. Excellent, excellent, excellent. And two more examples. Two more examples. Almost there. So the next one, n equals 1 to infinity of negative 1 to the nth power times 3 over 4n plus 1. Right, so obviously a alternating series. And can we figure out if this thing converges or not? Yeah, I think so, right? Because so the nth term, we'll use the alternating series test. The nth term is 3 over 4n plus 1. What about the an plus 1 term? It's going to be equal to 3 over, and you'd have to write it like this, 4n plus 1 plus 1. Right, so let's be careful here. This would be 3 over 4n plus 5. So definitely we have a of n greater than or equal to a of n plus 1, right? Because 3 divided by 4n plus 1 is definitely larger than 3 divided by 4n plus 5, right? And that's going to be true for all n. Okay, and let's see here. So once we've got that piece, we got to look at the limit. The limit as n goes to infinity of 3 over 4n plus 1. Well, that's definitely 0. Okay, so the fact that, you got this piece here and this piece here, and together they imply that the series converges. Okay, so the series must converge. Okay, so that is the alternating series test, and that's from last lecture. And then the last example we'll look at is this one. So the sum n equals 1 to infinity of n plus 1 over 2n plus 1 to the nth power. Does it converge? Well, this is a beauty. Perfect for the root test, right? Everything is exponentiated by the n. That's the thing that's creating the uncertainty. The rest of it's really straightforward. So let's try this out here. Let's just take the absolute value of the nth root of the absolute value. Okay, so in this case, it's going to be n plus 1 over 2n plus 1 to the nth power to the 1 over n power. Right, and so we can see that that is n plus 1 over 2n plus 1. And that's the nth root of the absolute value of the nth term. And so the limit is what we're interested in there. Okay, so the limit as n goes to infinity of n plus 1 over 2n plus 1. Well, that is another one, again, that I would hope everybody knows by now. Right, you've got two polynomials, first degree. The ratio of the lead coefficients is the limit there, so it's 1/2 less than 1. So the root test would say the series must converge. Okay, so there we go. We just went through about 5 or 6 examples in rapid succession of just pulling from different tests and different approaches, right? And so again, I can't state enough that this is the kind of thing that requires a lot of practice. You certainly aren't. I wouldn't expect anybody would be required in any course to memorize all of these tests. Maybe some courses. When I was an undergraduate and I took Calculus 2, I was not required to remember these, but it was hard enough just applying them. So I had access to notes where I had the tests written down, and that's how I did well in the course, just by being familiar with which ones to apply when and which ones I would have the most success with the least amount of effort. right? So, and then also just being able to interpret them, right? So sometimes, like some of the tests, they don't tell you whether something converges or not. They say, hey, if this limit exists, then the top and the bottom do the same thing, right? So if you know the top converges, then you know the bottom must converge as well, right? So sometimes the logic involved can be a little cumbersome, and so that's the thing that you really got to focus on understanding is like, when can I use these? What can I conclude from them? And then of course being able to apply them correctly. Okay, so that is it. Now next time, in the next session, we'll kind of shift gears a bit and discuss Taylor polynomials. So that's going to be Taylor polynomials and approximation, and then close on the heels of that it will be power series and Taylor series. And so these are going to be I think a high point of Calc 2. I also feel that just integration in general is a high point, but I do think power series is pretty interesting and cool stuff. So we'll end with a high note in the coming 3 or 4 lectures. So talk to you all then. Take care.